For more videos like this for discrete 1, you can take a look at Sarai Studies. Link is in the description box below. In one of the previous videos, I introduced the fact that a compound proposition, which we label as phi, this is the symbol phi, can either be a tautology, contradiction, or a contingency. And we simply figured this out by doing a truth table for the compound proposition. If all of the truth values for the compound proposition were true, then we say that it's a tautology. So T for true, T for tautology. For this compound proposition, all of the truth values were not true, so it's not a tautology. And in that video, I showed you how to prove if it is a tautology or not using truth tables like we see over here. But there's another way you can prove if a compound proposition is a tautology or not, and that's by using known equivalences. So let's say we're asked to show or prove, same thing, that this compound proposition is a tautology. Again, two ways, truth table and using known equivalences. First of all, how many columns do we need? Well, we have two propositions disregarding any and all operators. We just have P and Q, so we're going to have two columns, one for each proposition. Then I can split this up. So I'm going to do one column for P and Q. I'm going to do one column for P or Q. And instead of writing this over here, I'm just going to label this as 1, label this as 2. So this is 1, this is 2, and just be like, okay, this is now going to be 1 implies 2. How many rows do we need? Remember that the number of rows is equal to 2 to the n, where n is the number of propositions that you have. We only have 2 propositions. It's going to be 2 squared, which is 4, so we're going to have 4 rows. Now, how do we fill in the truth table? We take the number of rows divided by 2. 4 divided by 2 is 2, and then we keep dividing by 2 until we get to 1. We got to 1, so we're done. This tells me how many truths and falses I'm going to have to start off with, and you want to start with your truths, so you do 1 true, 2 truths, you used up all your truths, you move on to your falses. 1 false, 2 falses. Used up all my falses, and there's no space left, so I move on to my next column. This tells me I'm going to start off with 1 true and 1 false. I used up all my truths, I move on to my falses. I used up all my falses, I still have some space left. What do? I copy and paste the exact same pattern that I already have written until I run out of space. I run out of space, so I'm done with this column. Then here we have P and Q. Remember that an AND operator will only ever give you true if this and this are true at the same time. So we're looking at P and Q, both of these columns, and we're looking for them to be true at the same time. That's going to give us true, otherwise false. So here the only time they're true at the same time is in this case, so this is going to be true, otherwise it's false. Here we have P or Q. Remember, an OR operator is only going to give you true if this or this is true. So only one of them have to be true. So again, we're looking at P and Q, and I only need to see at least one true. So here I see a true, the whole thing's going to be true. Here I see at least one true, so the whole thing is going to be true. Here I see at least one true, so the whole thing's going to be true. Here I see no true, so otherwise it's false. Then here I have 1 implies 2. So remember, with an implication, you're looking for when this is false. So this is column 1, so you're looking for when it's false. It's false here, here, and here, so it's going to be true here, here, and here. The only other way this could be true is if the definition of the implication is satisfied. What's the definition? If 1 is true, then 2 should also be true. What's the only one that does that? 1 is true here, 2 is true here, so then the definition of the implication is satisfied, so it's true. Then you ask yourself, is this compound proposition a tautology or not? T for true. Just looking for when all of the truth values are true. Are they? Yes, so it is a tautology. So we prove that this compound proposition is a tautology using truth tables. Now let's see how we do it using known equivalences. So zooming in, we're told to show or to prove that this compound proposition is a tautology. Then you have to remember, what does it mean for a compound proposition to be a tautology? It means that it's just always true no matter what. In other words, this just ends up always being true. So if tautology means true, we can replace tautology with true, and is a tautology we can replace with being equivalent. So we're trying to actually show that this compound proposition is equivalent to true, that at the end of the day, it ends up just always being true. That's what we're trying to show. So now you can go to what you're used to and say, okay, first thing I have to identify what's my longest, most complicated looking side. That's this side. It's definitely not this. This is the simplest as it can get. And then second is you have to realize, okay, now that I have that side, my goal is to get this side to look like the other side. So we're going to start off with this over here, and we're going to say, what can this be equivalent to using something from here? Well, I see an implication, so I know it's going to have to be something in here. I see one thing implies another thing. So here I see one thing implies another thing is equivalent to, opposite of that one thing or that other thing. So to color code so you can get a picture of what we're dealing with, this is P, this is Q. The result is going to be not P or Q. So get the template. You're looking at the not and the or. I'm going to have my not and the or. And the P just goes right there. So the P is going to be dropped down here. So I'm going to take that, put it there. And the Q also stays the same. I'm going to drop it down. And you always want to write down what you used. So we used this, but because it doesn't have a name, like a domination law, identity law, whatever, I'm just going to actually write the a known equivalence. This is just something that we know is already equivalent and we're allowed to use. Now the problem is this is still not looking like this side. So we keep going. We say, okay, what is this equivalent to? Well, I see a negation and I see parentheses. I'm really inclined to distribute. So when you see that, that's De Morgan's law. You can go through everything, or you can just say, we're literally distributing the negation to every single thing in here, including the sign. Negation means opposite, so the opposite of P is going to be the opposite of P. The opposite of an and is or. The opposite of Q is going to be literally the opposite of Q. So this becomes that, and then everything else can drop down. What did we use? De Morgan's law. This still does not look like this. So we continue. What is this equivalent to? Well, I'm looking at this and I see that I have P and then the opposite of P, Q and then the opposite of Q. And what's interesting is that I know that there's a law that has to deal with something and its opposite, but they have to be together. They have to be next to each other, either with an or an and. So then in my head, I'm like, okay, I should be trying to get P and not P together, or maybe Q and not Q together, so that I can use one of these laws. So the question is, what's the first step that I can take to get closer to that goal? Well, I have something or something, and here I also have something or something. So let's try using this one and see what we get. This says that whatever's here, in this case that's not P, is going to be the output as is. So we're just going to have not P, and then or, so we bring down this or, Q, and Q is what was here, so that's what's next to P. So that's not Q. And then we have another or, so we bring that down. R, and R is what was after this or, so that's this. So this is the associative law. And notice how it did help us get one of these pairs closer together. In this case, it helped us get not Q and Q a little bit closer together. But we want it even closer together. So let's see what else we can do. Well, there's this commutative law that says if you have something or something, something or something, then it's the same as you just switching them. So I'm going to drop all of this down, so not P or, and then I can simply just switch these. And that is a commutative law. And now what's interesting, because of order of precedence, just like order of operations in math, if you have 1 plus 2 plus 3, you can do 1 plus 2, or you can do 2 plus 3 first. It doesn't matter. So same thing here. We have P or Q or not Q. I can either do P or Q first, or Q or not Q first. I'm going to do this first. Why? Because I know that there's a law that says if you have something or its opposite, something or its opposite is always going to give you true. So I'm going to drop everything else down, not P or, and then this itself becomes true. And that is the negation law. So we use the associative and commutative laws to get this pair together so that we could use the negation law. Now this still isn't this, so we keep going. Here we have something interesting. We have something or true. So when we have something or true, it's always going to give us true. That's a domination law. So this itself just becomes true and everything else drops down. This still doesn't look like this, so we keep going. What is this equivalent to? Well, again, we have something or true. Something or true is always going to give us true. That's again the domination law. So this something or true is just going to be true. Again, this compound proposition we managed to prove through known equivalences that it's the same, it's equivalent to true. So because this compound proposition is always true, it satisfies the definition of a tautology, which is a compound proposition that is always true, no matter what. And so we're done with this little proof by known equivalences. So we do our little square. Now, one thing that I want to note is that here I showed all of the steps, but Garcia in lecture, when he was doing a similar example, he didn't actually show the associative and commutative step. So I'll show you what he did. So I'm going to go ahead and remove all of this. From here, he was like, okay, I see P, I see the opposite of P. I see Q, I see the opposite of Q. And we know that we have some laws regarding P and its opposite, or P or its opposite, and so on. So the goal is to get them close to each other, which we've already discussed. But instead of going step by step, what he said was, all right, you see these propositions? They're all separated by the same sign. So the order in which you operate does not matter. It's the same thing as if you had 1 plus 2 plus 3 plus 4. You can add it in that order, or you can add it as 1 plus 2 plus 4 plus 3. You could switch these, and that's fine. It's still going to give you the same result. So because they have the same signs, you can switch everything around. So because these have the same signs, the same operators, you can switch these around however you see fit. So again, because we know that there are some laws regarding when you have something and its opposite next to each other, I would want to group something and its opposite together. So I'm going to group not P or P, that's one, or not Q or Q. So notice nothing disappeared. I have the exact same number of ors that I had in the original problem, and I have the exact same number of propositions that I had in the original problem. I'm just rearranging because they're all the same signs, the same operators, so it doesn't matter. And what he did was he just called this step the associative plus commutative step together. So he didn't actually show the work from how he technically is supposed to get here. He was just like, yeah, it's common sense, let's just get here. But this is the actual proper way to do it if you were curious. But again, double check even with Garcia if that's still acceptable, because I don't know, you might be taking this in a few years. Anyway, from here you have something or its opposite. When we have something or its opposite, it's going to be true. That's the negation law. So this here becomes true. We drop down the or, and then again we have something or its opposite, so we know by the negation law that that's also going to become true. But this still doesn't look like this. So we keep going. How can we simplify this further? Well, this is an or operator. Or is only ever going to output true if at least one or the other is true. And we know that at least one is true, so it's going to output true. So at the end of the day, this is true. And so we managed to get this side to look like this, right? We started here, we managed to get all the way over here. And so because of that, we proved that this compound proposition is equivalent to this one. That at the end of the day, this just ends up being true. So it is a tautology because the definition of a tautology is a compound proposition that is always true no matter what. So we proved that this compound proposition is a tautology using a truth table and using the known equivalences. Here I showed full steps, and here I showed if you want to combine the commutative and associative steps. And that's it for this video. I'll see you in the next.